So I'm sure you guys are familiar with the story of the Hydra, right? It was a serpent that Hercules had to slay. And the idea was every time he cut off one of its heads, 2 heads grew back. So what we're going to do is we're going to play a Hydra game, but it's going to be a slight modification on the Hydra. So, you know, several thousand years have passed and the Hydra has evolved. And so now we're going to have a Hydra that whenever Hercules cuts off its head, at the nth slice, it grows back n heads. Right? So this is going to be the idea with this Hydra. So the first time he cuts off a head, it grows back 1 set of heads. The second time, it grows back 2. The millionth time, it grows back 1,000,000 set of heads. Right? And our question is going to be, how can we slay this Hydra? So first I want to kind of set up the ground rules. So I'm going to introduce the Hydra game. Okay, so we're going to represent our Hydra as a graph. So we're going to have a bunch of nodes and a bunch of edges connecting these nodes. Right? So the Hydra is going to be represented as a graph. But more specifically, it's going to be a type of graph that's called a rooted tree. Right? So by a rooted tree. Right? So the idea is going to be the following. Basically, you have one node in your graph. I'm going to draw a bunch of examples in a second. You're going to have one node in your graph that is, we're going to call the root. This is going to be the body of the Hydra. And then you're going to have a bunch of necks growing out of this. And from those necks, you're going to have a bunch of heads. Right? The idea behind a rooted tree is that any 2 vertices in this graph, any 2 nodes in this graph are going to be connected by exactly one path. Right? So for example, this is an example of a Hydra. We'll have a root down here. This will be our root. This is the body of the Hydra. And then we'll have one neck here, and maybe 3 heads growing out of this neck. Then we'll have another neck here. There'll be a series of segments that look like this. So 1, 2, 3, 4, 5. This is another neck. These top nodes are going to represent the heads, and these are going to represent necks. And then maybe we'll have another set of heads over here. Right, so we'll have a set of heads that maybe looks like this. Right, so this is an example of a Hydra. This is going to be called a root. Any one of these guys is going to be called a node. Right, any one of these circles is going to be called a node. Any one of these lines connecting 2 circles is going to be called a segment. Right, so for example, this thing right here is going to be called a segment. These nodes up here are going to be called top nodes. And this segment here, any segment connected to a top node is going to be called the head, a head of the Hydra. Right? So this is a head, 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 this is a head. Right? So this Hydra has 1, 2, 3, 4, 5, 6 heads. Right? And they're all connected by these necks. When we chop off heads on this Hydra, we're going to be chopping off at these segments. Right? So we're just going to be removing this head. Right? So this portion is going to be called the head of the Hydra.
Are there 7 heads or 6?
Oh, there's 7. There's 1 at the bottom, too.
Oh yeah, there's a 7th one down here. Thank you. Yeah. So 1, 2, 3, 4, 5, 6, 7. Right? There's a tiny little head down here. Okay, so this is an example of a Hydra. Right? This one looks kind of complicated. We can write down some similar examples. Right? So here's another example. This is a really simple Hydra. This is a 3-headed Hydra, for example. And then we could say, well, what is an example of a graph that won't be a Hydra? What is an example of a graph that's not a rooted tree? Well, we could write an example that looks like this. So, I don't know, we could say maybe it has a bunch of heads over here, and something that looks like this. This is not a Hydra. Right? The point is that any 2 nodes have to be connected by a unique path of segments. Right? This is not the case here. Right? So this is an example of something that's not a Hydra. So our Hydras are going to look like this. Okay, so what are the rules of this game? Right? How does this Hydra grow its heads back? Right? So the idea is going to be we're going to chop off these heads. What are the rules? So the rules go as follows. So I'll write down a set of rules, and then we'll do an example. We'll draw a Hydra and chop off a bunch of its heads. So step 1, Hercules severs a head. Once he severs a head, what we're going to do, so he's going to chop off this head, for example, right? This node, I'm going to call this node the stump, right? Whatever's left over after you chop off a head, we'll call this node a stump or something. What we're going to do is he's going to chop off this head, and we'll look at the stump, and we'll go one node beneath it, and we'll look at this subtree that contains the stump, and draw a bunch of copies of it on that node. So for example, if I chopped off this head, and that's my 100th cut, I'm going to look at this head right here, or this subtree right here, and draw 100 of them over here. Right? So this is going to be the idea. So let me kind of write down this formula, write this down a little formally. So go to the node, right below, the node connected to the severed head. And what we're going to do is reproduce n copies of the subtree containing the head stump at the selected node. Right, and here n is the number of times Hercules has already attacked the Hydra so far. So the first time it's going to grow back 1 copy. The second time you cut off a head, it's going to grow back 2 copies. The third time it's going to grow back 3 copies, so on and so forth. So n is equal to the number of times Hercules has already attacked. So this is our setup, right? So let's do an example. Okay, I'm going to start with this Hydra, and we'll go through an example. We'll chop off 2 of its heads. Well, maybe not this example. Maybe I'll write a slightly easier to look at one. So let's do an example to show you guys how this works. What I'm going to do is I'll draw the new heads in red. Right? So every time a new set of heads appears, I'm going to draw them in red. So let's look at an example. Let's look at this one. So here's a node, a node, a node, a node. One set of heads is going to grow out from this node. And then we're going to have another set of heads growing out of this node. And then maybe another set of heads growing out of here. Okay, so we have a Hydra that looks like this. And so we can kind of pick a node at random and chop it off. Pick a head at random and chop it off, right? Let's chop off this one and see what happens. Right, so what I'm going to do is I'm going to chop off this head. What that means is now, this is my first cut, so I'm going to go to this node right here, and I look at the node that contains this guy's stump, and I see what's left over. I see the subtree here. It's a graph with 3 heads, and I'm going to reproduce 1 copy of this graph that's left over attached to this node. Right, so this thing that's left over after I've chopped off the head, I'm going to produce 1 more copy of it here. Right? So after 1 chop, we have a graph that looks like this. Okay, so it's going to be 1, 2, 3, 4, going up. Here we're going to have the same set of heads that was there. Here we're going to have the same set of heads that was there. Here we're going to have this head, we're going to have this set of heads, but now it's missing this guy. And this set of heads, and it's missing this guy. And then we have a new set of heads identical to it that grows back. Right? So this is the new set of heads that grows back. Okay, so after 1 chop, we have a Hydra that looks like this. It just grew back 3 heads. Right? We cut off 1, it got 3 more. Okay, the next step you might think is, okay, let's chop off another head. Let's maybe chop off a head over here. Right? Let's look at this lowest thing and chop off a head. So what I'm going to do next is I'll chop off this head, let's say. So what do? Well, I erase this head, and I look at what's left over, and since this is my second chop, I'm going to have 2 copies of this thing grow out from this node. Right? I always go down 1 node, I go down to here, and I draw 2 copies of this thing. Right? It's my second cut, so I draw 2 copies. If it was my third cut, I would draw 3 copies, so on and so forth. Right? So if I do my second cut, the top of the Hydra, all this stuff is going to remain the same. Right? So these guys will stay the same. We're just going to have a bunch of new heads down here. So we have 1, 2, 3, 4. Right? These guys are all the same. These guys are all the same. This guy, we've removed one of his heads. Right? But now we're going to grow back 2 copies. Right? So what I'm going to do is draw 2 copies of this thing. I'll draw 1 copy up here, and 1 copy down here. Okay. So we've chopped off 1 head, we've just got 4 more. Right? So the natural question to ask is Hercules doomed? Right? Is he doomed to fail this? If he keeps chopping off heads, can he ever succeed? So the question we're going to ask is there a best strategy for killing this Hydra? You know, is there a way he can, you know, select heads and kill off this Hydra? What do you guys think? For people who don't know the answer already, what do you guys think? Is there a strategy to do this? Does it seem like it might be a hopeless cause? Because if you think about it, after you chop this thing 10 times, it grows back 10 copies of whatever stuff is left over. Right? After you chop this thing 1,000,000 times, it'll grow back 1,000,000 copies. Right? So you got a whole bunch of heads. And you can imagine if you start with a more complicated Hydra than this, it's going to be a complete mess. Right? Okay. So, any guesses? Yeah.
Will there not be enough space to continually?
Okay, that's a good question. So, assuming you have like assuming you're working somewhere where there's an infinite amount of space and you could fit as large of a Hydra as you want. Yeah, no, you're absolutely right. But so we're going to try to answer this question. How can Hercules kill this Hydra? That's going to be the point of the talk. Yeah, do you have
Can he like punch the side of the mountain and bring the rocks down to crush it?
No, he only has his axe or his sword or whatever, and no matter how many times it chops, it's going to stay sharp forever, and he's just going to keep chopping away at this Hydra. He has an infinite amount of time. It's a really ideal situation, right?
I thought
Okay, what's up?
that is hard.
Yeah, stab his heart. Yeah, if you can, right? If you can get past all the heads. You're going to fill the room with heads first. Okay, so the question is, how do we address this problem? So in order to address this problem, what I want to introduce is I want to tie it into another problem. It's a thing called Goodstein sequences. One of the things you notice is the number of heads that we're going to have on this Hydra, if we keep chopping, it's just going to blow up, right? I mean, here we added 3 heads. Here we added 4 heads. If we do another chop, right, if I were to chop off this thing, I'm going to add 6 more heads. So it's this sequence of heads that's just going to grow. Right? It's going to be this huge number of heads that's going to grow. So what I want to do is tie this thing to what's called a Goodstein sequence. It's a similar type of problem. So let me define for you guys what Goodstein sequences are. So these are sequences in the sense of calculus 2 and analysis, right? It's a sequence. It's going to be a sequence of natural numbers. So let's talk a little bit about what these sequences are. They're pretty easy to define. So they're going to be Goodstein sequences. Okay. So the idea is going to be the following. We're going to take a number, a natural number, and write it in what's called hereditary base 2 notation. So we're going to write it as a sum of powers of 2, but the exponents in those powers of 2 will also write in base 2, and the exponents of the exponents will write in base 2. Right? So for example, let me just write down, this is called hereditary base 2. If I take a number like 266, I can write it in base 2 as 2 to the 8 plus 2 to the 3 plus 2. And then I could say, well, 8 is a number that's not written in base 2. Let me write 8 in base 2. 3 is a number that's not written in base 2. Let me write 3 in base 2. Right? So what I can do is I could say this is 2 to the 2 to the 3 plus 2 to the 2 plus 1 plus 2. And then I'm left with, well, 3 is not written in base 2. 3 can be written as 2 plus 1. Right? It's 2 to the 1 plus 2 to the 0. So I can write this as 2 to the 2 to the 2 plus 1 plus 2 to the 2 plus 1 plus 2. Okay, so this is called hereditary base 2. And you could do this for base n. You could write things in hereditary base 3 where everything's written in base 3. Base 4, you could write everything in base 4. The idea is basically you want to write everything in base 2, right? Write it as a sum of powers of 2. And then any of the exponents, rewrite them as a sum of powers of 2. And then any of those exponents, rewrite them as a sum of powers of 2. Right? Okay, so to define a Goodstein sequence, what we're going to do is we're going to take all the 2's that occur here, replace them with 3's, and subtract 1 from the number, then rewrite it in base 3. Then we're going to take all the 3's, replace them with 4's, subtract 1, rewrite it in base 4. Right? We're going to generate a sequence this way, and this is going to be called a Goodstein sequence. Let's start with a simple example. Right? Let's start with like the number 4. So we form a sequence as follows. So the first number, I'm going to call it G1. I'm going to start with the number 4. Right? Realistically, we could start with anything. We could start with 5, 6, 7. We could start with 266 for all we care. I'm starting with 4 because 4 is going to be an easy example to start with. If I say write this thing in base 2, what would you guys tell me? Write it as a sum of powers of 2. 2 squared. Right? You'd say this is 2 squared. Okay. So this is how you write this thing in hereditary base 2. It's really easy. Right? So what do? The idea is take all the 2's, replace them with 3's, subtract 1 from the number, and then rewrite it in base 3. Right? So replace all 2's with 3's. Subtract 1. And then rewrite in base 3. Rewrite in hereditary base 3. Right? So if I do that, I get this number G2. This is going to be 3 cubed. Right? I replace the 2's with 3's. Subtract 1. So this is going to be 26. And then I take 26 and rewrite it in base 3. Right? If I rewrite this thing in base 3, I get 2 times 3 squared plus 2 times 3 plus 2. Right, so this is how you rewrite this number in hereditary base 3. Okay, next step, we take the 3's, replace them with 4's, subtract 1, rewrite it in base 4. Right? That's going to be the next number. So we're going to build up a sequence this way. So the next step is replace the 3's with 4's, subtract 1, and rewrite in base 4. Hereditary base 4. Right? So G3 is going to be, well, let's do that. Right? We'll replace these 3's with 4's, so it'll be 2 times 4 squared plus 2 times 4 plus 2, and then we're going to subtract 1. So it's really just plus 1. Right? It's going to be plus 2 and then minus 1. So this thing's already in base 4 for us. We don't need to do anything. Right? This is already written in base 4. And we get this number. This is 41. Right? And you guys can imagine how this goes. We're going to replace the 4's with 5's, subtract 1, rewrite in base 5. Replace the 5's with 6's, subtract 1, rewrite in base 6. Right? So if we keep doing the same thing, G4 is going to be 2 times 5 squared plus 2 times 5. This is the number 60. G5 is going to be 2 times 6 squared plus 2 times 6 plus 5. We rewrite it in base 6. So on and so forth. This is 83. If we keep going, G6 will be 109, so on and so forth. Right, so we get the sequence, and you might be thinking, okay, big deal. It's a sequence. What does it look like it's doing? Does it look like it's converging to anything? Not really, right? It looks like it's diverging. So big deal. What can we say about this sequence? So what I want to show you guys is something a little more interesting. We started with 4. 4 is relatively small, and it looks like the sequence is growing pretty slowly, right? I mean, we have 4, 26, 41, 60, 83, 109. You know, it looks like it's growing pretty slowly. It looks like it's diverging. What if we had started with the number 19? Right? What happens to the sequence if we start with a number like 19? Like if we start with a really big number? Let's try it. Okay? Let's try to write 19 this way. So what if we start with 19? Right? So G1 will be 19, and we could write it in base 2, right? Hereditary base 2 is 2 to the 2 to the 2, plus 2, plus 1. So we're going to take the 2's, replace them with 3's, subtract 1. So G2 is going to be 3 to the 3 to the 3, plus 3, and then plus 1 minus 1. And that's already in base 3 for us. Do you guys have any idea how big this number is? It's much bigger than 19. Any guesses? Yeah, so actually this number is approximately equal to 7.625 times 10 to the 12th. Okay, but let's keep going, right? Let's replace all the 3's with 4's, subtract 1, rewrite it in base 4, right? So G3 will be 4 to the 4 to the 4 plus 2. this is going to be, if you compute it, it's approximately 1.3 times 10 to the 154. Right, a huge number. Let's keep going. G4 rather. Right, this is 5 to the 5 to the 5 plus 1. This is approximately 2.6 times 10 to the 36,305. G5, if we were to keep going, it's about 10 to the 700,000. Right, so it's somewhere in that ballpark. Right, so this is a huge. This sequence blows up to. It looks like it blows up to some really huge values. So the interesting thing about the sequence is it actually converges to 0. No matter what number you start with, if you define the sequence, it's always guaranteed to converge to 0. And that's going to be what we try to prove today. And we're going to tie it back to the Hydra problem, right? Because just like this sequence blows up really quickly, the Hydra's number of heads seem to blow up really quickly. So the idea behind, killing the Hydra and showing that this kind of sequence converges to 0, they're going to involve similar ideas, right? So the question is going to be, how do we show that the sequence converges to 0, right? And not only does it converge to 0, I mean, it goes to 0 in finitely many steps, right? So eventually the sequence just becomes 0, 0, 0, 0, 0, 0. Right? So this is what's called Goodstein's theorem. So Goodstein's theorem. Says the following: the Goodstein sequence. So this is called the Goodstein sequence of a number, right? This is the Goodstein sequence of 19. This thing we were writing here was the Goodstein sequence of 4. The Goodstein sequence of any natural number converges to 0. Of any natural number converges to 0. Okay, so how the heck are we going to tackle this? One of the things I want to state is something called the well-ordering principle. So if you guys have had discrete, you might know what the well-ordering principle is. We're going to state a version of it that is pretty intuitive. I mean, well-ordering principle is pretty intuitive itself. But if I give you a strictly decreasing set of natural numbers, right? So natural numbers are numbers 0, 1, 2, 3, 4, 5, 6, 7, 8. If I give you a strictly decreasing set of natural numbers, what can you tell me happens to that set of natural numbers eventually? So like any number in the sequence is always less than the one before it. So it's like a strictly decreasing set. Any guesses as to what might happen? So if I gave you a sequence starting at the number 10, and I said the sequence is strictly decreasing, and it's an infinite sequence, what do you expect the 20th term of the sequence to be?
Negative.
It's natural numbers.
For 0?
It's going to be 0, right? Because if you start with 10, the next number in the sequence has to be less than 10. Right? The next number in the sequence has to be less than that. The next number in the sequence has to be less than that. Eventually the sequence terminates and just becomes 0, 0, 0, 0, 0, 0, 0. Right? So this is the version of the well-ordering principle we're going to use. Right, so we'll state this well-ordering principle. As follows. If xn, let's say n goes from 1, or let's say n goes from 0 to infinity, is a strictly decreasing sequence of natural numbers then that sequence terminates. Then the sequence terminates in finitely many steps. In finitely many steps. Okay, so we might get this idea now. We might. What I'm claiming is that this sequence, this Goodstein sequence that we've been defining over there, converges to 0, right? So the question is going to be, can I bound this sequence? Can I bound these numbers? Right? Can I find numbers greater than the things in the sequence in order, such that the bounds form a strictly decreasing sequence? Right? That's going to be the question we ask. So you could say, okay, can you find a number bigger than 19, and then a number smaller than that one, but bigger than this guy, a number smaller than that one, but bigger than this guy, a number smaller than that one, but bigger than this guy, such that we could form an infinite decreasing sequence of natural numbers. Right? Can we bound this some way? So at first you might think I'm crazy, because this sequence looks like it's blowing up. Right? You might think, well, I probably need huge numbers, right? You just told me that the next number is something like 10 to the 700,000. The next number after that is probably much, much bigger. The next number after that is probably much, much bigger. So you'd be right, right? So can we bound these g's by a decreasing sequence? If we can do that, if we could put some sort of sequence over here, like this thing is greater than 19, this thing is greater than 19, and this sequence is decreasing, then this has to terminate. Therefore, this thing has to terminate. Okay, that's going to be the idea. So we, like I've been saying, we probably need huge numbers to do this, right? And what I'm going to actually do is use numbers so huge that they're actually going to be infinite numbers, right? I'm going to extend the natural numbers to something called the ordinals, and I'm going to use infinite numbers to bound the sequence. I'm going to use a sequence of infinite numbers to bound this, right? So the question is, how the heck do we define these infinite numbers? How do we define a collection of numbers bigger than the naturals, in some sense? Okay, so let's kind of define the ordinals as follows. So, we define ordinals as follows. These are called the ordinal numbers. Okay. So first things first, we have a bunch of natural numbers. We have 0, 1, 2, 3, 4, 5, blah, 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 blah. Right? So we have 0, less than 1, less than 2, less than 3, dot, dot, dot. Okay, so then you might ask me, well, what do I do? The sequence of natural numbers kind of goes on forever, right? The string of inequalities. What I'm going to do is I'm going to define this number called omega. Omega is going to be bigger than all the natural numbers. Right? It's going to be a number that's bigger than all the natural numbers. Right? So I'm going to define this thing called omega. So omega is a number, I'm going to put this in quotes, bigger than all the naturals. All the naturals. Right, this is going to be a number bigger than all the naturals. Okay, great. This can be done rigorously, by the way. This is not just something I'm making up with my imagination. This is all rigorous. It can be done rigorously. Okay, if I want to take a number, so I define this number as bigger than all the naturals. What number should come next? If I give you a really large number and I tell you what comes right after it, what do you tell me? Omega plus 1, right? So we'll define omega plus 1. What comes after that? Omega plus 2. Okay, and after we define all the omega plus n's, what do you think comes after that? Omega plus omega, right? We're going to call that 2 times omega. Right? So the next number here is going to be omega plus omega, and we'll call this guy 2 times omega. Okay, we can keep going. What comes after 2 omega? 2 omega plus 1, right? So we can keep going with this, and maybe I'll use this space here. Right? So what comes after this? You would tell me 2 omega plus 1. What comes after this? 2 omega plus 2, right? What comes after all of these guys? What comes after the 2 omega plus n's? 3 omega, right? Omega plus omega plus omega. So 3 omega. Okay, after we've exhausted this list of, 2 omega, 3 omega, and all the numbers in between, what do you guys think comes after that?
Omega squared.
Omega times omega, right? Omega squared. Right? So the next number is omega squared. Well, not the next one. There's a bunch of stuff in between, but then we have omega squared. Okay, and then we have omega squared plus 1, omega squared plus 2, omega squared plus 3, blah, blah, blah. What do you think comes pretty far after omega squared?
Omega to the omega.
Well, before omega to the omega. You're right, you're right. What about before omega to the omega? We'll get there in a second. Omega cubed, right? So we go on, there's a bunch of numbers in between. We have omega cubed, right? Then we keep going, we can form omega to the 4th. And we keep going with this, we can form omega to the omega, right? So there's a bunch of stuff in between. We could form omega to the omega. Okay, and then you can imagine we can keep going from there. We could keep going and form omega to the omega to the omega, and omega to the omega to the omega to the omega, and so on and so forth, right? So we can just keep going with this. Omega to the omega to the omega, so on and so forth, right? These numbers are called ordinals. These are the numbers we're going to use, right? So natural numbers are all examples of finite ordinals. This number is the first infinite ordinal. It's actually the set of natural numbers. This is that guy plus 1, plus 2, so on and so forth. These are all called infinite ordinals. They're an extension of the natural numbers. The interesting thing about them is that this collection eventually gets so big that it's too large to be a set. Right? That's how many of these things there are. So we're actually going to use these guys to bound our Goodstein sequences. here's the interesting thing about ordinals. So natural numbers, we said, have this well-ordering property, right? If I take any sequence of natural numbers that's strictly decreasing, that sequence terminates in finitely many steps. The ordinals, as an extension of the naturals, retain that property. The ordinals are actually well-ordered in this way as well. Right? So we actually have this property, and we'll do an example in a second. We actually have the well-ordering for ordinals. Right? So we could say if xn, n going from 0 to infinity, is a strictly decreasing sequence of ordinals, it terminates in finitely many steps. Right, so this will go to 0 in finitely many steps. We can illustrate this with an ordinal. Let's pick something like 3 omega and show that if I have a decreasing sequence starting at 3 omega, that decreasing sequence will eventually go to 0, right, in finitely many steps. So 3 omega, this is our first ordinal. That's going to be like over here somewhere. If I ask you guys to give me something in the sequence that's less than 3 omega, what would you tell me? 2 omega, maybe plus some natural number, right? It seems like all the things below 3 omega are 2 omega plus some natural number, right? Maybe the next thing in the sequence might be like 2 omega plus n, right? So for some number n. Would you guys agree with me that if we were to continue going, we'd hit 2 omega in finitely many steps, right? Because the next thing has to be at most 2 omega plus n minus 1, the next thing has to be plus n minus 2, so on and so forth. So in finitely many steps, we'd hit 2 omega. Right, so this would be done in finitely many steps. Right, because each time we're just going to be subtracting off a natural number. Okay. So we just have 2 omega plus a natural, and this sequence is decreasing, so those naturals will go to 0 in finitely many steps. Can you guys give me a number smaller than 2 omega? What's a number smaller than 2 omega? Maybe omega plus some m, I don't know, right? The next thing would be like omega plus m. And then we get another sequence that goes down to omega, and this happens in finitely many steps. Right? And then once we're down to omega, what's a number that's less than omega? Well, 0 is one of them, but like some other natural number, right? And once we have a decreasing sequence of naturals, that terminates in finitely many steps also. Right? So the idea behind these ordinals is they retain this well-ordering property. If I start with any ordinal and I form a strictly decreasing sequence of those guys, it's going to go to 0 in finitely many steps. This example kind of provides the intuition behind that. Right? It's kind of like if we start with 3 omega, the next thing has to be 2 omega plus something. Well, that's going to go to 2 omega in finitely many steps. The next thing beneath that has to be omega plus something. Well, that's going to go to omega in finitely many steps. The next thing beneath that has to be some natural number, and that's going to go to 0 in finitely many steps. It's strictly decreasing. Okay, so now we do what I promised you. We're going to take the Goodstein sequence, and we're going to bound it by a sequence of ordinals. Right? So let's try to do this. So what we're going to do is we're going to show that that sequence that we defined, I'm going to do the one we did for 4, can be bounded by a decreasing sequence of ordinals. Right, so let's try to remind ourselves what the Goodstein sequence for 4 looked like. Right, so here we have G1 was 4. We said this was 2 squared. Right? G2, let me just rewrite these guys so we have them, is 26. And we said this was 2 times 3 squared plus 2 times 3 plus 2. G3 was 41. This is 2 times 4 squared plus 2 times 4 plus 1. G4, sorry, this is 41. 60, this is going to be 2 times 5 squared plus 2 times 5. Right, if we keep going, G5 is 83. This is 2 times 6 squared plus 1 times 6 plus 5. G6 is 109. This is 2 times 7 squared plus 1 times 7 plus 4, and so on and so forth. Right? This is a Goodstein sequence for 4. You could do this for any Goodstein sequence you want. So now the question is, what ordinal can we bound this by? Well, first thought I might have is, this is 2 squared. Let's bound it by omega to the omega. Right? You guys would agree with me that omega to the omega is bigger than 2 squared, right? Fair enough. Omega to the omega. Okay, what can we bound this guy by? Well, here we took all the 2's and replaced them with omegas. Let's try to do the same thing here. Let's take all the 3's and replace them with omegas. Right? So this guy is going to be less than 2 times omega squared plus 2 times omega plus 2. Right? And this ordinal is less than this ordinal. You guys would agree, right? Omega squared and all the stuff added to it is over here somewhere, and omega to the omega is over here. So this guy's definitely less than that. Okay, what would you guys bound this guy by? If we follow the same patterns. Here we replace all the 2's with omegas, here we replace the 3's with omegas. What would you guys bound this guy by? Yeah, maybe replace all the 4's with omegas, right? So do 2 times omega squared plus 2 times omega plus 1. Okay, great. This one is less than this one, right? What about this one? What would you guys do? Yeah, replace the 5's, right? We do 2 times omega squared plus 2 times omega. Great. This guy's less than this guy. What would you do here?
6.
Yeah, replace the 6's. So you guys get the pattern, right? And this is how the proof works in general. I'm not going to get into the nitty-gritty of the proof itself, but this is how the proof works in general. Notice this guy is less than this guy, because this guy is, they both have a 2 omega squared, but this has 2 times omega, and this has omega plus 5. Omega plus 5 is smaller than 2 times omega, right? 2 times omega is like over here, omega plus 5 is like over here in these dots somewhere, right? And you can imagine how this goes. This is 2 times omega squared plus omega plus 4. And you get the idea, right? You end up with a decreasing sequence of ordinals. Right? And you could show that no matter what number you start with, this sequence of ordinals, take the first one, replace the 2's with omegas. Take the next one, replace the 3's with omegas. Take the next one, replace the 4 with omegas, and so on and so forth. No matter what number you start with, you get a decreasing sequence of ordinals here. Right? By our well-ordering theorem, this sequence goes to 0 in finitely many steps. Therefore, this sequence has to go to 0 in finitely many steps. Right? That's the idea behind the proof. So this is the idea behind the proof of Goodstein's theorem. Right? This sequence of ordinals is strictly decreasing, so it goes to 0 in finitely many steps. Therefore, this guy has to terminate in finitely many steps. It's weird, I know. The interesting thing is, this cannot be proved within Peano arithmetic. You need ordinals to prove this. Right? So if you try to use just the theory of the natural numbers to do this, you cannot do it. It's impossible. It's provably impossible. So we need ordinals to actually prove this theorem. So this is one of these cool things. So now the question you might be asking is how does this tie back to the Hydra? Right? What does this have to do with Hydras? Right? We have one big sequence of numbers. We showed that it goes to 0. What does that have to do with the Hydra? So let's kind of show how this relates to the Hydra problem. So what I'm going to do is draw a Hydra, and I'm going to chop off one of its heads, and we're going to pretend that this is the millionth cut, or something like that, or maybe like the 100th cut. So it's going to grow back 100 copies. So what's the idea? Let's draw a Hydra. So this is the very first one that I drew in the beginning. So 5, 2, 3, 4, 5 heads here. We're going to have another set of heads here. We're going to have a head growing out here, and a set of heads growing out here. So this is the very first Hydra that I drew. Right? You guys remember this is like the very first one we saw. So what we're going to do is we're going to label all the nodes, and what I'm going to do is assign an ordinal to each one of the nodes. Right? So all the heads, I'm going to assign a 0 to them. Right? So I'm going to take all these heads and assign a 0 to them. Then I'm going to go down, and I'm going to look at the next node and say, well, how many heads are attached to that node? Right? This guy has 3 heads, so I'm going to put a 3 over here. This guy has 1 head attached, so I'm going to put a 1 over here. This guy has 2 heads attached, so I'm going to put a 2 over here. This guy I'm going to ignore for a second. I'll explain why. It's a little more complicated. I'm going to ignore it for a second. What's that? Yeah, I mean, I ignored it before by accident. I'm just going to ignore it again. I'm going to put a 0 there, but I'm going to ignore what happens to this one just for a second. Okay, what I'm going to do is I'm going to go down a node, and I'm going to label this guy omega cubed. I'm going to take omega to whatever's up here. Right, so this guy's going to be omega cubed. This guy's going to be omega to the 1, which is just omega. And this guy right here is going to be omega squared. Right? Then I'm going to go down a node, and I'm going to label the next node omega to whatever's up here. Okay, so this node's going to be omega to the omega. right? If I have two nodes coming in to another node, what I'm going to do is I'm going to take omega to this power plus omega to this power. So this is really going to be omega to the 0 plus omega to the omega squared. Right? It's omega to this plus omega to this. And so this is really 1 plus omega to the omega squared. And then I'm going to go down one more, and this node is going to be labeled omega to this guy plus omega to this guy plus omega to this guy. Right? So this last node is going to be an ordinal. It's going to be omega to the omega cubed plus omega to the omega to the omega plus omega to the 1 plus omega to the omega squared. Right? That's going to be an ordinal here. Okay, so next question. Let's chop off one of the heads and see what happens to this ordinal. Right? The thing we want to focus on is the ordinal that appears at the root. Right? Remember, this is the root. This represents the Hydra's body. We want to focus on this ordinal here. What do you guys predict might happen based on what we've seen so far? If I chop off one of the heads, what do you think is going to happen to this ordinal? It's probably going to be smaller, right? If I'm comparing it to Goodstein's theorem, maybe we want a decreasing sequence of ordinals, so maybe that'll end up being smaller. Let's try it, right? Let's try it. Okay, so I'm going to chop off, I don't know, in my notes I have this head chopped off. So what I'm going to do, chop off this head. And I'm going to pretend it's my 100th cut. Let's say this is my 100th step. I've already done 99 cuts. This is my 100th cut. So what the Hydra is going to do is grow back 100 copies of this segment right here. Right? It's going to grow back 100 copies. Let's see what happens. I'm not going to draw 100 copies, obviously. But let's see what this thing looks like, right? So we have most of the Hydra remains unchanged. Right? Most of the Hydra remains unchanged. This is unchanged. This is unchanged. There are 5 of these, right? 1, 2, 3, 4, 5. This little head is unchanged. But what ends up changing is I'm going to remove this guy. So I'm going to take this thing and produce 100 more copies of it. Right? So I'm going to leave the original head here. And then maybe I'll draw it in yellow or something. I'm going to include 100 more copies. Maybe 100 of these guys. Yeah, dot 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 represents all the others. Right? But the point is, let's say this is the 100th cut. It doesn't matter what cut it is. This is like the 100th cut. We've gotten the Hydra down to this point, and now we have this many heads. Okay, let's try to write down the ordinal that we get by using the same kind of thing. Right? So here we have 0, 0, 0. Here we have 3. Here we have omega cubed. Great. Here we have 0, 1, omega, omega to the omega. So this all stays the same. Here we have 0. Let's see what we get here. Here we get 0 on all these heads. So we're going to have 100 zeros over here. Here we're going to have 1s. There's going to be a bunch of 1s. What goes down here? Yeah, it's going to be omega to the 1. Right? It's going to be omega to the 1 plus omega to the 1 plus omega to the 1 plus da 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 plus omega to the 1. We're going to have, since this is 100 copies, we're going to have 101 omega down here. Okay, so the next question is, well, what goes over here? Well, it's going to be omega to the 0 plus omega to the 101 omega. Right? You're going to get 1 plus omega to the 101 omega. And now the question is, well, what goes down here? Down here we're going to get omega to the omega cubed plus omega to the omega plus to the omega plus omega to the 1 plus omega to the 101 omega. And you would agree with me that this ordinal, you would hopefully agree with me that this ordinal is smaller because omega to the omega squared is definitely bigger than omega to the 101 omega. Great. So we end up, by chopping off heads on this Hydra, what you're actually doing is you're, in some sense, decreasing the complexity of the Hydra. Right? The idea is you're decreasing the complexity. It looks messier, but in some sense you end up decreasing the complexity, and this is represented by a decreasing sequence of ordinals. Right? And every time you chop off a head, the ordinal that gets represented at the root gets smaller. So the idea is, well, you have a sequence of strictly decreasing ordinals, or a strictly decreasing sequence of ordinals. That sequence has to go to 0 infinitely many steps. Therefore, you end up killing the Hydra. So use the well-ordering principle again.
Oh, wait.
Yeah.
So you said you rate code 99 times, though. Wouldn't that be like explosive like that?
What's up?
You said you cut it down 99 times already.
So let's say I've chopped the Hydra's heads 99 times,
Yeah.
and I end up with a picture that looks like this.
Oh, really?
And I take my 100th cut, right? I take this head, this is my 100th attack on the Hydra. So what happens is, he keeps this part of his head, but then he grows 100 copies of that thing out here. So there's like 100 copies of the
There's
same.
like 99 copies out somewhere.
What's that?
99 copies out somewhere else.
He can. I mean, if you have heads attached to here, and you cut one off, it just disappears.
Oh.
Yeah, so it doesn't grow anything back. So the way you kill the Hydra is if you have a head attached to here, you would want to grow something back from a node that doesn't exist. Right? So the way you cut off the heads is by paring them down until you get down to here, and then just cutting them off this way.
Oh, so
Right.
like.
So like if you had a bunch of heads attached here, you just chop them off and done.
So
Yeah.
you cut off you cut off a single head.
Yeah.
So like, there's only one head for every.
Yes.
Other 100. So you cut off those, that's you can't grow another one back.
So if you cut off like anything that's attached to here, it can grow another one back. But you're only allowed to chop at the top. You're not allowed to chop down here. That's the point. Yeah. But when you chop, what you do is you grow back from this node, right? So this is the stump. You look at the subtree containing the stump, and you grow back copies of that subtree. Okay. So now the question is there a best strategy for killing the Hydra? The answer is it doesn't really matter. You can just go in there. Hercules can go in there drunkenly and just start slicing all over the place, and he'll kill the Hydra eventually. Right? That's the answer to the question. The Hydra will always die. Yeah.
Chris, what if instead of the 100th cut, that was his omega cut?
Oh no! We're assuming he can only do finitely many. then you might have a problem. You're absolutely right. Okay, so that's it.